Everyone. Morning. Hope you're doing well. Yes, the fireplace is back. Um, I was looking around at different backgrounds, and this one is just the best, I think, blend of it's not too distracting, but it's vibey as well. So yeah. I use this setup at my day job meetings, and I was getting feedback like, "Are you a streamer?" No. We'll just wait a few more minutes for people to trickle in, and then we'll get going. Thanks, Maria. Uh, yeah, I'm a tech streamer at a college, I guess. How was everyone's week or weekend? Did they do anything interesting? As we're trying to use up a few more minutes, waiting for people to trickle in. I've just been working, so nothing too crazy. All right, seems like we have 10. So let me, I think that's a decent time to start. And let's get going. Sorry, I'm mildly distracted, but let me share my screen. All right. So many windows. So today we're going to jump into raster data proper, or this weekend. Um, sorry. What do you mean, Renee, this weekend? Sorry, I lost the context. Is that about what you did this weekend, or maybe
Yeah,
last
yeah.
weekend?
I just joined as you were asking, but I was wondering if you're asking about this weekend.
This and or last. It kind of just depends. Yeah.
Oh, okay, yeah, I was just gonna say. I mean, you're jumping into the lecture now, but I saw Khruangbin in concert last night. That was pretty cool. I don't know if you know them.
No.
They're a very funky band.
Okay. Cool.
Check it
Share a
out.
link in chat. Yeah, so that others can have a listen. Yeah. Thanks. Actually, I'm going, speaking of this weekend, I was thinking about last weekend, but I'm doing a pottery class tonight. So that'll be
Oh,
fun.
nice,
Yeah, there's
nice,
like pizza and beer. And so you just like hang out for a few hours and it's at a bar. So I'm like, okay, cool.
nice. Where do
Yeah.
you live again?
I live in 29 Palms, California.
Oh, okay, cool,
It's near
cool.
Joshua Tree, but
Yeah,
it's out in the desert. Yeah.
that's a cool area.
Yeah. I dig it. Cool. Did anyone else have a fun weekend or plans for this weekend? If not, we'll jump into lecture. I guess this could be your fun plan for this weekend. I'm not gonna lie. I'm not gonna discount that maybe this is the shining light in your week that you look forward to waking up and hanging out on Saturday mornings. But maybe not. And I won't take it personal otherwise. Uh, all right. That awkward silence lets me know that we should get into lecture. Um, Raster spatial data with Python. So this is kind of a continuation of where we left off last week, pivoting to kind of the one of the other sides. It's not like a binary vector and raster. There's kind of some in-betweens and it gets complicated, but um, two of the main popular flavors of data, uh, raster is kind of this other one that it's really more where we're starting to get into the remote sensing side of things. And so today, I believe we're gonna dabble with an application of remote sensing in the more environmental focus, so monitoring tree growth, I believe. If you haven't noticed, I'm kind of a plant nerd, so that's where a lot of this course kind of focuses. Well, that's hot, but it's good. Um, so if you're interested in more urban or developed applications of remote sensing, do let me know, and I'll try to find some kind of supplementary content that we can discuss in class. But a lot of these exercises kind of lean into the remote sensing for the application of kind of studying environmental conditions. Um, so let's jump in. And before we actually jump into content, uh, I wanted to do a few quick reminders. Also, shout out to whoever told me to look at the Google slide themes. I've done it before, but yeah, it is better than nothing. So reminders, we're kind of already coming up to the end of the semester, even though we just started. Um, I didn't realize, or I guess I knew, but I forgot how quick these sessions go. And so we're kind of at the halfway point already. Uh, so um, I just wanted to call out kind of the remaining schedule for the semester and remaining lab assignments. This doesn't include any extra credit opportunities and just different, mainly extra credit opportunities that'll throw your way. But just wanted to remind you all so you don't feel like you're getting um, surprised by assignments. But this week is remote sensing, kind of the basics of understanding raster data. Next week, we're going to jump into LiDAR data. Um, Following that, multispectral data, so kind of image information that has more than 3 layers of data. So not just red, green, blue, but kind of a variety of flavors of information that tell you different things about the natural and built environment. And then we'll kind of cap it out with a lab on spectral indices. That's kind of leveraging multispectral data and then kind of distilling it, extracting more useful information out of it, and creating these kind of formulas that you can reuse in different environments with tweaks, of course, but to kind of help simplify analyses. And then that's our final is May 18th. So we have like a month. So I just wanted to remind you all that the end is near. Um, don't don't fall too behind. If you're behind on any lab assignments, uh, don't hesitate to turn them in ASAP just because you'll get fewer points deducted and that's just better for your grade. Um, Kind of speaking on lab assignments, this lab that we're gonna kind of walk through today is due next Saturday before 9 a.m. And then we have 3 more lab assignments, which are due kind of a week after they're assigned. And then the final is going to have a due date of May 19th before midnight. And so you'll have about uh, like 30 hours to work on it, but it'll really take you less time than any one of these lab assignments. So I just wanted to give you a heads up what to expect, and also open the floor for any questions about your expectations on any of the remaining labs or the final. I guess as a shouldn't encourage you to look ahead, but if you want to, go for it. Have fun. But all the labs are already kind of linked out there. So if you want to get an idea of what's coming up, or if you know you'll be out a week and you need to get ahead, um, go for it. You won't be able to turn it in on Canvas until, or whatever it's called, until I guess the open date. But yeah, see a question from Andrea. Will we have lecture on the 18th? No. I mean, we'll have like uh more like the segue, like, hey, what's up? Um, kind of like the awkward icebreakers hangout that I try to do every time, and then it'll just be the exam. In terms of advice for the exam, I will share a study guide, um, maybe in like a week or two. I just need to sit down and kind of think about that a little more, but I will prepare a resource that should tip you off in terms of everything to expect. I think that um, you were here for the last semester, and so the final, I don't want to say it was easy, but it was like fairly easy. Um, and so I'd say it's in the vein of like it's going to be fairly easy, but I'm not going to hold your hand. And so I'm not going to ask you to do anything I haven't asked you to do before, but I'm not going to just tell you how to do it also, if that makes sense. Because to me, that's like the time, okay, we've been vibing, we've been working hard all this semester. Now, like, show me what you've learned. And so that's kind of how I view the final. And I think that you're all capable of like crushing it and getting 100% or more. And I see there's a graduation at 10 a.m. that day. Um, I was not aware of that. But yeah, well, you have basically until the 19th at 11:59 p.m. So hopefully that gives you plenty of time. You don't have to be there. It's more just it it kicks off then. I'll make the repo public so that people can see the test basically. But yeah, cool. All right, let's get back to lecture, unless there's other questions, but that's really just kind of reminders for the rest of the semester. So just three more, or including today, four more lab assignments, and then the final. And then sprinkled throughout there, you'll have extra credit opportunities. And hopefully that kind of supplements your learning and also gives you opportunities to get some more points. Okay. Ah, what is happening? Technology is not my friend. Okay, lab outline. So today it's kind of mirroring a lot of what we did last week, but applied to raster data so that we're getting a lot of that kind of foundational context on how to open and explore files and better understand the tasty geographic metadata tidbits that we need to know, like uh, projection information, stuff like that, extents, like what units the data is in, and how we can then uh, potentially transform it as necessary or not for certain analyses, and then using that raster data with vector data. And so today we're kind of um, a lot of it's foundational to raster data, but then we're leveraging some of what we did last week to then kind of build on our learnings and integrate it further. And we're just going to do some common operations. I already mentioned reprojecting. We'll also look into cropping raster data. So maybe you have a massive remote sensing data set for the continental United States, but you just need to crop it to a specific region. Yeah, we'll learn how to do that today. And then we'll also learn how to classify uh, remotely sensed data. I don't exactly remember what classification kind of scheme we'll be using, but it's a way to group information to make it more useful. And this is the moment you've all been waiting for. Code word for extra credit opportunity for today in class. Yucca Shitagera. Probably did not pronounce that right, but this is a plant that I see pretty frequently in my neck of the woods out here in the Mojave Desert. So make sure to go to Canvas, input that code word into the extra credit assignment for, or it's not extra credit, it's just attendance assignment for today, and put that in. Let's code. Second time you heard that word. Okay, Gareth, I need to know the context of where you heard it the first time. That's so random that like,
Honestly, I don't know. I just remember I was just working at my desk at Esri and I just hear someone say like, "Oh, I went to Joshua Tree," and then pronounce that the scientific name for it.
oh yeah, okay, nice.
I was like, I heard that before.
Okay, funny, funny. Cool. All right, let's code. Unless there's other questions from the lecture. Ever see a teddy bear Choya? I'm pretty sure I have. Um, I don't know that I could necessarily tell you where, but I was my in-laws were visiting like a month ago or so. And so we went to the Choya Cactus Gardens in Joshua Tree and just generally we're Choya hunting or spotting because my mother-in-law, that's her favorite uh like plant that she saw out of anything. And so we were always like looking for that. Yeah, they
They're
don't
so
have those
funky
in
looking.
Pennsylvania. Yeah, they don't have those. They're starting to flower now. I'll take a picture and try to send it to you all, but they have like a lemon lime kind of light green flower. And so it's very strange. But yeah, the desert in spring is pretty. Yeah.
They jump out at you too. I've been
Uh,
attacked by one.
oh no, it was bad.
Like the spines.
Oh,
Yeah.
they also collapse off of it. Like there was a child, like we were on a hike and or it's like a nature observation trail, the Barker Dam, and there was like a 4 or 5 year old kid that had grabbed a cholla with her bare hand.
Oh gosh. I still
And
have
it's
a
just
scar
like,
in my
yeah,
leg from
it's
it.
horrible. Like, yeah, I was just cringing looking at it. That, yeah. And
It hurt.
her poor dad having to do the struggle. Oh my goodness. But yeah, desert plants they're very cute, but they're also very pointy. Um, yeah. All right, raster spatial data with Python. Let's do this. Let me open the chat again. My sister sat on one. Oh my God. Bless her heart. That's horrible. That's yeah, that's bad. All right. Before we jump into actual coding, let's just walk through the lab just to kind of build some confidence in what the task at hand is and that we can kind of crush this easily. So we're gonna create a repo, a GitHub repo called lab3 or blah, 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 lab3. Oops, that it should be 606, my bad. Oh well, actually I'll edit that right now. When copy paste goes wrong. But we're going to be creating a repo in GitHub that we're going to save our work to. And then we're going to use this GitHub Codespaces Jupyter repository as a template, kind of like what we've been doing this whole semester. Then we're going to use the GitHub UI. Actually, we're going to skip this step too, because I did not prepare those ahead of time for you. So we'll punt that to next week. That's okay. Changes on the fly happen. It's the beauty of life. Some improvisation. Um, so we're going to skip number 2, and then we're going to open that repository in our GitHub Codespace, or it's going to create a new codespace for us. And then we're going to follow these labs, kind of like what we've been doing this whole semester. A lot of this work will be fairly similar to what we've been doing, especially last week, but then there's also going to be some new kind of raster specific things that we haven't encountered before. As we work through these notebooks, we're going to make sure to commit our changes to the repo. And then because I'm kind of paranoid, I will double check the actual GitHub repo for myself every time, like I do each week. Feel free to skip that if you don't want. And then you'll submit the link in Canvas, and you'll get all the points because you're going to turn it in on time. So I'm going to edit that last URL again, or the repo name, because I copy pasted some of these instructions from last semester. Apologies. But yeah, let's get into it. I'm going to stop share and then reshare my GitHub view so that it's a little easier, just because I need to see these instructions and not get lost. And I'll share the link to the Jupyter, or the Codespaces Jupyter repo. You might have it saved in your web browser history, but if not, I'll share it in chat. And then I'm going to share my screen. Okay, cool. Let me make this a little wider. All right, great. So let's use this template and create a new repository. So we're using this as our template. We don't need to include all branches. We're just going to use the default branch, which is likely main. And then as per the instructions, let's call this lab GISC 606 lab 3. Don't need a description. Let's get going. Make sure it's public. Create the repo. And also feel free at this point, if you prefer working alone or not while I'm talking over your thoughts, you can hop off. Just wanted to remind you all of that. You don't have to stay. And then from Andrea, is it okay to choose a name? The repository GIS 602 Lab 3. Yeah, it's fine. As long as I was just kind of trying to make it so that you could copy paste the name and it would work, but just do whatever works for you as long as you submit it into Canvas. I'll check that, whatever repo is called. Okay, great. Now the instructions have updated. If you refresh your course webpage for today's lab instructions, it should have been updated with the new repo name, the removed step 2, and all that goodness. So now let's open the repository in a GitHub Codespace. You do that by clicking Codespace, and then let's create a Codespace on main. Shout out to my brother-in-law. He works at Bumperman. This is a nice Yeti. It's nice. All right. So I'm gonna unshare. Actually, no, I'll do some tab management. So you can see that it's installing things, getting us ready for the day. Once pip has installed all the dependencies that are defined here, let's create a new notebook called intro to raster.ipynb. Okay, cool. So feel free to use the file explorer, this area, and do like right click or control click, depending on your browser or mouse situation, new file. I like using the terminal and just creating files that way. So I'm going to do touch intro to raster.ipynb. And remember from last semester, we used touch to kind of create empty new files. We could also use nano if we weren't in this kind of pretty code editor environment, but we're not going to do that. And usually you don't use nano for something like a Jupyter notebook. It just makes things kind of ugly, hard to read. So as you can see, the kind of notebook view is now asking us to select a kernel. This is just because it might not really make sense, like why, like it's just Python. You can have different kernels for different languages. You can have different kernels for different versions of Python. So Jupyter notebooks are kind of really cool in that way that it's kind of this common environment that you can reuse across a lot of different workflows and types of coding teams. So that's why it's kind of this extra like annoyance of having to pick. But we'll just pick the trusty, tried and true Python 3.10.13 that we've been using throughout the semester. And now you can see we're ready to run code. But at this point, we don't actually know what to run. So let's go over to CU Boulder's Intermediate Earth Data Science textbook. So we're gonna start with open, plot, and explore raster data with Python and Xarray. So we're already talking about a library that I don't think we've used yet, Xarray. So should be fun. But today, and shout out to the Earth Lab, this is a really awesome resource for learning Python specific kind of remote sensing thingies. They call it Earth Data Analytics, but it's really kind of applied remote sensing for the most part, but with Python. And so today we're going to open, plot, and explore raster data with Python, handle no data values in raster data, create plotting extents so that you can plot raster and vector data together with matplotlib. This is what we've kind of been using so far this semester, and then exploring raster data using histograms and descriptive statistics. Okay, so actually, let's go to the intro to raster data. I might have, yeah, I was supposed to walk through this first. My bad. I think there's just no code in this one. So this is an overview of raster data. So let's walk through this first and then go back to that next one. Apologies for skipping that. So we're going to learn kind of fundamental concepts of working with raster data in Python, including understanding spatial attributes of raster data, how to open the data, access the metadata, and explore the distribution of values in the data set. And so we're going to use Python to mainly access geotiff data, but these techniques are applicable to a variety of raster file data types, whether it's like netcdf. I don't know about IMG just because that it might be proprietary, but yeah. So we'll need a computer, but we're already set up with that. So we need we're not going to do LiDAR today, but we will previously or in a subsequently, like next week. So let's skip this here. I guess we'll learn how to plot LiDAR raster data in this lesson, but it's kind of a derivative data set that's more of a raster than a point cloud. And so what is a raster? It's a grid of data that are stored as a grid of values rendered on a map as pixels. So, I mean, it's like a photograph or an image. But it's instead of kind of how you take a selfie or something looking out, it's from the down or from above looking down. There can also be oblique imagery, but that's kind of a little more an advanced use case. We're going to entirely focus on just nadir view kind of from above imagery looking down like a satellite or airplane would see. So a raster file is just composed of a grid of these cells all of which are the same size. And then they're just representing data at those different kind of locations that the grid is overlaying. And so I'm guessing you've used an application like Google Earth or Google Maps, but we're not necessarily doing that today. But that kind of gives you an idea of some of the like raster data types. You can see kind of imagery, like true color imagery using Google Maps. But with remote sensing, it's not really a photograph because they're actually spatially referenced. And so each of those kind of points in space is kind of, you can do more accurate geolocation type analyses on that data as opposed to like a photograph, which is kind of just, there might be a point location of where the photo was taken, but not each individual pixel having a location. And so the pixel represents an area of land on the ground predominantly. It could be trees, water, you name it, depending on what the kind of sensor is observing. And the area is defined by the spatial resolution of the raster. So how coarse or fine grained those kind of grid cells are. Back in the old days, not the old days, but like in the old days of remote sensing, maybe a few decades ago, it was hard to get anything below a few 100-meter resolution, like squares. Whereas now you can get sub-foot data. It's kind of crazy. And then with drones, you can get like centimeter level resolution on the pixels. So it's pretty wild how far we've come in terms of what's possible with collecting remotely sensed data. But it's important to kind of start somewhere. So I think today it's going to be dealing with a little more coarse data because it's just easier to compute. If you have really fine-grained data, that's going to take a lot more processing power on your computer because there's just so much more information for the same amount of space. So a few raster facts. Each cell is called a pixel. Each pixel represents an area on the ground, and the resolution of the raster represents the area that each pixel represents on the ground. So a 1 meter resolution raster means that each pixel represents a 1 meter by 1 meter area on the ground. And so here you can see how the same extent is represented at 4 different resolutions. So you can see that it's kind of hard to tell what this is, but I guess if you already knew what you were looking for, you could tell, oh yeah, this is trees versus not trees. And then the finer you get, the more easy it is to kind of detect what's happening. But that comes at a cost because however many data points there are here, there's just multiple times more on each of these. And so you have to pay for that in terms of storing it on your computer. And whenever you run a process or an analysis on it, it's going to be slower and just be more expensive, to use kind of like an industry term, or I mean, an academic term too. And so let's learn how to open a raster data set in Python. They say it's a LiDAR raster data set because it's a derivative of LiDAR data. LiDAR data, which we'll cover next week, is it's a different type of sensor that lets you get more information about the structure of objects. But it's super, super big data, really expensive to compute and just run analyses on. And so researchers and practitioners often create kind of derivative data sets from those point clouds that are just 2D rasters. And then you can infer and do different kind of analyses with those 2D data sets. And that's what we're going to be using today, is one of those products from originally a LiDAR point cloud, but it's kind of a derivative product. So let's get back to this lesson that I kind of preemptively started on. So we're going to learn more about working with LiDAR derived. Yeah, it's a derivative raster data set. And so it's going to be representing the terrain and the elevation elevation of the Earth's surface, and the surface elevation, the elevation at the tops of the trees, buildings, etc., above the Earth's surface. And if you want to learn more about how LiDAR is used to derive these surface models, you can stay tuned for next week because we'll cover that. But like I said, the point cloud LiDAR is attached to airplanes, whatever, satellites, drones. It's blasting energy down. It's not like harming people, but it's like shooting light, and then that bounces back up, and the sensor detects information from those pulses back. And they don't, the kind of energy that the sensor emits doesn't all return at once. And so depending on what's below the sensor, whether it's a tree, a building, a car, just plain bare earth, those kind of, the energy returns at a different speed. And so the sensor is then able to kind of reverse engineer what it's seeing based on how fast things are returning and how much is returned, because also these objects absorb a little bit. And so you can see here kind of a simplified diagram of these points. This is kind of, imagine there's an airplane with a sensor blasting radiation down, not like bad radiation, but just like light. And then it's kind of bouncing off of these surfaces. So here it's hitting these shrubs, hitting the treetops, some of it's passing through and then hitting the ground and then bouncing back. And then it's kind of, as you go over this image, there's this kind of different surfaces are being kind of described. From that, you can kind of create these derivative products of the digital terrain model and the digital surface model. And so you have this digital surface model minus the digital terrain model is the canopy height model. And so this canopy height model is super useful for ecologists and foresters for tracking kind of forest health and just information about tree stands. So here's a little tidbit about those data. DSM, DEM, and CHM are the most common raster format LiDAR-derived data products. One way to derive a CHM is to take the difference between the digital surface model and the digital terrain model. The CHM represents the actual height of trees, buildings, etc., with the influence of ground elevation removed. So we got a little teaser about what's to come next week in terms of LiDAR data, but let's get started with some derivative or LiDAR data derivatives. So I'm going to return back to our code environment and let's import some stuff. We might have to install some things too, but that's part of the fun. So let's get started. Error messages are how you learn. Import OS. MPy as MP. Import map. I don't see any questions in the chat. But if you have any, feel free to unmute or write them in chat. Import Seaborn as SNS. And then I don't think we have any, we don't have GeoPandas, Rio X-Array, or EarthPy. So let's install those. I'm going to import these first. Let's do pip install. Actually, let's use this pip. When you put an exclamation point in these notebook environments, it kind of tells the computer to run this as a bash script and not as Python. And so it's kind of like a cheat code a little bit. So we're running pip install GeoPandas, Rio X array, and EarthPy. Okay. So it's just installing all this stuff into our. Awesome. Okay, cool. Now let's import those things. import GeoPandas as GPD, import Rio X array as RXR, import EarthPy as ET, and then let's set some slightly nicer plotting with Seaborn. SNS.set font scale equals 1.5. And then let's do style equals, let's actually look up Seaborn styles because I always forget what options there are. So let's kind of just take a peek. They actually have like somewhere there's like they'll show all of the options that you can pick from. The themes. The options are illustrated in the aesthetics tutorial. Figure styles. Okay. There are 5 preset Seaborn styles. Dark grid, white grid, dark, white, and ticks. So that's white grid, dark. Now let's do dark grid. Okay. Thought there were more. Okay. Feel free to pick whatever style you prefer. Now let's download the data and continue working. So I'm going to use EarthPy to get the data using the data get data utility. And this is really like, it's more useful for learning. I think EarthPy is actually developed in conjunction with this textbook. I could be a little wrong, but I'm pretty sure they're somehow affiliated. And we're using our familiar OS Chadir OS path join, and then ETIO home, Earth analytics, data. It's downloading the information and we're good. Okay, cool. Took a second. I was worried. It's like, is my internet dying? So we have our data. Now let's define the path to the DEM. And this was created using data from the National Ecological Observatory Network, NEON. So props to them. And so let's open that data. So I'm going to call it DEM pre-path equals OS path join, Colorado flood. And so this is the DEM before a flood. We're also going to load the DEM after a flood. And so one of the types of analysis that you can perform using these types of data is comparing or determining the extent of kind of deforestation from a flood event. How much has changed as a result of some kind of natural hazard event. You could also do this after like an earthquake or like a fire. I mean, the earthquake might not affect trees, it might topple buildings, but you could do that with a digital surface model of an urban area. I'm sure there's more sophisticated like AI methods to like determine precise like damage extent, but for like a quick, just like you need information now. That's probably still a pretty good way. So we defined our path for this file that we downloaded in the previous code cell. So now let's read that in using Rio X array. This is kind of it's the mongrel child of Raster IO and X array. Rio is short for Raster IO. And so it's kind of those two projects have this interesting kind of like child project that takes powers from both of them and puts them together. And you get Rio X array. So we're going to use that to read in this TIFF data. But you can also use Rio X-Array to open other types of raster data, which is why it's pretty flexible and nice. So Rio or DTM pre-array or R equals RXR, open raster IO, DEM pre-path. And then let's like print out what that looks like. And you can see I'm already making an, oh no, that's not an error. Okay, DTM. Okay, cool. That might be an error. I'm not sure. Okay. So we read in the data, and you can see that there's just some metadata that it outputs. It's a little fancier though than GeoPandas. So they kind of have a slightly interactive uh, experience, but it's just telling you information about data contained within. But you can see it's kind of related to pandas as well. And so there's some interoperability, which is really nice. So the data array that we just created with X-array, this DTM pre-ARR, is it has the raster data in a NumPy array format. It has spatial metadata, including the coordinates reference system and the spatial extent. And then it has any other metadata. And so we can print out some of this information using some helper attributes that Rio X-Array just automagically creates for us. So we can get the coordinates reference system or the coordinate reference system of the data just using the .rio.crs attribute. So let's do dtm.prearr.rio.crs. And so you can see that's the coordinate reference system. We can get the spatial extent using the rio.bounds method. So let's do the same. I'm using tab complete just so I don't have to type everything. In case you're wondering how I can magically like spell words out. So we got the spatial extent. We can also get the no data value so that we know how the, I guess, data creators are kind of indicating this in their data set. So let's do DTM pre-R Rio no data. So it's this massive negative number. Rio X-Array also gives you built-in plotting functionality, kind of like pandas and GeoPandas do, which is really nice. So you have a similar kind of workflow, even when you're dealing with raster data. It's slightly different, but it's close enough where I feel like it's kind of comfortable and familiar. And it's leveraging PyPlot kind of behind the scenes. So the figures even look similar to what we're used to. So this data is supposed to represent the terrain model data, but you can see the range of values is like not what we expect. So this data is supposed to be for Boulder, Colorado. And the elevation there can range anywhere from 1,000 to 3,000 meters, which is pretty high elevation. And here it's -3 to 3. And so it's just like there's something wrong, something's going on. So let's look at the distribution of pixel values, because right now our data is not really rendering as we expect. So let's do some sleuthing, some Sherlock Holmesing to determine if there's something that might be causing this, and if there's a solution that we could maybe deploy. So let's do DTM pre-array or R plot, and then we're going to plot a histogram, and then let's use the color purple. And then we'll use PyPlot to show it. So here's the histogram for our LiDAR DTM. And so you can notice that the values that are below 0, this suggests that there may be no data values in the data. And remember how we checked the no data value here. And it was something large. -3 times 10 to the 38. That's a really big number. So let's actually better inspect this using NumPy. Or not better, but differently inspect the data. So let's get the no data min and the no data max, or not, or that's phrased wrong. Let's get the min and max of the data set, including no data values. So we'll do that using NumPy, nan min. You can see it returns the minimum of an array or minimum along an axis. So let's do np nan min DTM free ARR dot values. And dot values returns a NumPy array of your data. So let's do that. Let's see what it returns. So as we expect, the no data value is the max, or the minimum actually. Similarly, let's do the max. And so this is 2,087 meters, which is also kind of reasonable. If the elevation of the study site is between 1,000 and 3,000 meters, I expect that something like this would make sense. So let's do some more exploration. So we know that there's no data values in our data set, and it's skewing the plot of our colors. That's why it's just like, it's messed up. So there could also be outliers in our data. So let's see if we can improve our plot rendering with some Python trickery. It's not really trickery, but it's just some like tweaking you can do. And so you can account for no data values. And then the Raster IO and matplotlib rendering magic will nicely display your data. So let's try that out. Okay, so let's inspect the data set, because multidimensional data sets can often cause issues with rendering. So you kind of have to like squish and squeeze and tweak them a bit so that they fit nicely into the visualization library. So you can see that this has a 1 at the beginning. So it has this extra dimension that we don't really need. It's saying it's like a one-dimensional data set, 2,000 by 4,000. We don't need to know this. We just need the 2,000 by 4,000 aspect. So let's open this data, mask the no values, and then squeeze it. So we're going to reduce that third dimension because we only have one dimension to begin, or one layer here anyway. We don't need to like track that. We can just have 2,000 by 4,000. So let's do that. So DTM pre R ARR equals RXR open raster IO. And then we're going to use that DEM pre-path masked equals true. That's how you know to account for the no data values. And then we're going to say squeeze. And then let's output the new shape of our data set. Cool. So that's exactly what we want. Now let's plot this data and see what it looks like. Fingers crossed, it looks a little better. So we're going to use pyplot again, the subplots method. So f ax equals BLT subplots, fig size equals 10 by 5. DTM pre-ARR dot plot. CMAP equals, how about we do purples? AX equals AX. Then let's do some figure formatting, namely setting the title and making it a little prettier looking by turning off some axes. So ax.set title LiDAR digital LiDAR DEM. I don't feel like typing everything. /n for a new line. Folder flood 2013. Let's set the axis off. And then let's show it with pyplot. It's thinking. Nice. So you can see that our data looks a lot better now. Our legend magically understands that we don't need to like render it in scientific notation. And the data of interest is actually residing in this kind of 1500 to 2500 range of values. And it actually kind of displays what we might expect to look in the natural environment, not just a blank, totally monotone data set. This looks a lot more realistic and believable. So let's inspect the histogram now. Let's see if that has changed since we've kind of read in the data differently. So again, I'm gonna use pyplot subplots. We're gonna make this fixed size 10 by 6. Again, we're gonna use the DTM pre-ARR and plot it, but we're gonna invoke the hist plot. Let's make it pink. And let's put 20 categories or 20 bins for the data. And then let's set the title. This histogram of data with no data values removed. Guilty show. Cool. So you can see that a majority of values are kind of in this range here, the 1700-ish. And it kind of tapers off the higher you go. There's a noticeable bump here around 1900. So let's now check the minimum and the maximum to see if our values are more believable for like a natural elevation and not -3 times 10 to the 28. That would be very, very deep. So NP Nanman, BTM pre-array, data, nice. And then NP NanX, DTM pre-array data. Okay, cool. Believable. So now that we've kind of gotten some usable raster data read in without the no data values, let's plot it with some vector data and get our first experience of using vector and raster data simultaneously with Python. So we're going to add shapefile overlays to our data. Let's use GeoPandas to do some shapefile reading. So I'm going to create some file paths. The reason I don't just put in the local path on my computer into the file name is because depending on the operating system, that could break. So using OS path join magically kind of handles that for us across systems. There's other libraries that do a similar thing, but this is a tried and true. Cool. Clip extent dot shp. Cool. So we have our site boundary path. Now let's read that in with GeoPandas and then plot it with PyPlot. Site bound shp gpd file site bound path. And then let's plot it. It's PLT subplots. 8x4 site bound shp dot plot color equals teal edge color equals purple ax equals ax to the title. And then let's display it. Cool. It's a rectangle. Now let's actually overlay that rectangle onto our raster data set. And then that'll be the conclusion of this first sub lesson for today. So f(ax) equals PLT subplots, big size equals 11x4. Let's do DTM pre-array dot plot plot.im show. So we're learning all these different kind of plotting methods. CMAP equals, let's do it purples. AX equals AX. Site bound SHP dot plot. Color equals no, oops. Yeah, I forgot. I fat fingered it, accidentally ran the code. It's all good. Edge color teal. Line width equals, let's make it thick. Z order, it's 4. I think that's to bring it to the top. And then AX equals AX to the title. Raster layer with vector overlay. AX axis off. PLT show. Magic. A beautiful, stunning raster vector overlay work of art. So we're getting our experience manipulating, inspecting this data set. Let's save this notebook, commit it to the repo, and then keep going. I don't want to commit to always, at least today. Okay. I'm now going to inspect my repository to make sure that, in fact, changes were committed and they were awesome. Does it look good? Looks great. Okay. Let's get back to code. Now we're going to create a second notebook called plot histograms, and we're going to get more experience plotting raster histograms. So I'm going to use touch to create a new file called plot histograms.ip inb. Now let's open that. We're gonna, again, use the Python 3.10.13 kernel. And then let's pivot to the code or to the instructions. So we learned about some key attributes of raster data in the previous lesson, but now let's really dive deep into histograms and how they're used to better understand the distribution of data. So that was actually a really quick overview. So let's jump into the code. Okay, so we're again going to be using Rio Xarray, EarthPy, NumPy, Seaborn, PyPlot, OS, all that good stuff. So let's import those. OS. Okay, import Seaborn as SNS. NumPy as MP. Import Rio X array as RXR. Import EarthPy as ET. So ET data, get data. Actually, we don't need to do that because we already have the data, but I will set the kind of working environment. Earth analytics data. And then let's use Seaborn to set the font scale and the style. Now we're ready to get started. Let's define the relative path to the pre-DTM TIFF and then read it in using Raster IO. Path join, Colorado flood, spatial, Boulder Hill, or Boulder Lee Hill, RD, pre flood, LiDAR, pre DTM, that TIFF. That's long. Okay. So now LiDAR, DTM path, or DTM IM, because RXR, open raster IO, LiDAR DEM path. And then let's output the shape. Cool. 1 by 2000 by 4000. Perfect. See you, Talissa. Cool. Now let's do some raster histograms. So the histograms that we're going to create in a second represent the distribution of pixel elevation values in our data. And so this is useful to identify outlier data, assess the min and max of values in our data, and just to explore the general distribution of elevation in the data. Is it generally flat, hilly, or is it high elevation, low elevation, you name it. You can kind of just get at a glance kind of feeling for the study site. So it's often good practice to view histograms of your data before beginning any work, because it is kind of a pre-data exploration step, and they'll tell you a lot about the values in your data before you do any kind of more sophisticated coding. And they'll also often help you identify issues associated with processing your data, so things to maybe look out for or to consider. And so below, let's start by looking at the shape of the histogram. And we're going to notice that there's going to be a skew in our data. And oftentimes a skew like this, with many values on one side of the plot, means that there's an outlier in our data, or there's missing data values that we need to deal with. So we're kind of almost didactically going into the problem we already solved in the last lesson, removing the no data value, but we're going to really use histograms to better understand this problem. and how in real world applications this occurs often. So let's plot a histogram. I'm gonna use plot subplots. Big size 10 by 6. LiDAR DM IM plot hist. AX equals AX. Color, make them teal. And then let's set the title, X label, Y label, and then display it. Distribution, spelling. Distribution of LiDAR DEM elevation values. X label equals elevation in meters. And then the Y label, frequency. And then let's use PyPlot to show it. So I'm actually going to set it onto white grid because it's easier to actually measure. The Seaborn styling, I get why they did that now. Cool. So you can see it's a little under 1, a little over 7. So there's a no data value skewing the histogram. It's this thing here. Like it shouldn't be -3 times 10 to the 6 meters elevation. That would be very deep. Very deep. So it's skewing our data. So this is a problem that can occur when you're using raster data sets. I mean, a variety of data sets, but it's very apparent here. And so generally speaking, now we're kind of zooming out. What does a histogram even tell us? So it shows us how the data is distributed. In this case, that there's kind of this massive skew to it. Each bar or bin in the plot represents the number of pixels or the number or frequency of pixels that fall in that range specified by this bin. So this bin here is this kind of like below 3-ish bin, represents a lot. Here, it's this kind of around 0-ish bin represents the rest of the data. And this is probably the useful information that we need. And so you can use the bins argument to specify fewer or more breaks in your histogram. So let's, before we go on to masking the data set, let's see if we can't specify more bins on this data set using bins equals, let's make 20 bins. And you can see that even with that, the skew is it's pretty significant. What if we do 50 bins? No, okay. So that's the extent. So let's actually read in our data again with the no data masking, like we did in the previous lesson. So we'll specify masked equals true, and that'll fill any no data values. Or it'll mask any fill or no data values, excuse me. So let's do that. LiDAR DMM equals RXR. So we're overwriting that variable we had in our memory, but this time now masking it. Masked equals true. And then let's plot it. LiDAR DMIM dot plot dot hist AX equals AX, color equals teal, bins equals 30. And then I'm just going to skip the title showing or the title specifying because I don't feel like typing it. But you can see that this much more accurately represents our data. This is kind of the same result we saw in the previous lesson, but now we're not dealing with this massive -3 times 10 to the 6 meter data set or data points. So we removed a lot of that skew. So now let's customize our histogram and make it a little more kind of specific to our needs. So we can actually make custom bins, and we're going to do that so that we can kind of chunk the data into larger regions that we specify. And by region, I mean like elevation regions. So like the region between 1600 and 1800 meters, 18 to 2000, and then 2000 to 2100 meters. So let's customize our histogram. Fix size 10 by 6. LiDAR, DEM, IM, plot, hist. AX equals AX, color equals pink. Bins equals, and so now these are the bins that we're kind of bucketing the data into. So 1600 to 1800, and then 1800 to 2000, and then 2000 to 2100. So let's hit the title at least. Distribution. LiDAR, DEM, elevation, values. PLT show. So here you can see that we're able to bucket our data or bin it into custom groupings. 16 to 18, 18 to 2000, and 2000 to 2100. So let's save our results, commit our changes, and get on to the next one. Don't hesitate to reach out if there's any questions, whether unmuting or in chat. Making sure to follow chat. Right? Verifying that it's there. It's there. Awesome. Let's return to our code space. Proceed with the next lesson. This one is diving into spatial raster metadata, namely coordinate reference systems, resolution, and extent. So let's create a new notebook called metadata.ipynb. Let's select the Python 3.10.13 kernel, and then let's proceed. Okay, cool. So we're going to learn about 3 important spatial attributes associated with raster data. Some of them we've already kind of been dipping our toes into, but we're going to really lean into it on this one. I have trouble saying that word today. Coordinate reference systems, resolution, and spatial extent. My tongue is tired, I think. I didn't get enough sleep. Okay, so coordinate reference systems. The CRS of a spatial object tells us in Python where the raster is located in geographic space. It also tells Python what mathematical method it should use to flatten or project the raster in geographic space. So when you're using other softwares as well that aren't Python, very similar kind of things happening. So you can see these maps of the United States in 3 different projections, and you can see there's differences in shape associated with each projection, and those differences are a direct result of the calculations used to flatten the data onto a two-dimensional map. And the source is from opennews.org. So what makes spatial data line up on a map? We're going to discuss coordinate reference systems in more detail in a bit, but let's just remember the data saved from the same location, but saved in different coordinate reference systems will not line up in any GIS or other program unless there's like on-the-fly reprojection. But that's another kind of special case. And so when you're working with spatial data in Python, it's really important to identify discrepancies in CRS so that you can line things up and make sure your data is accurate for analysis. So let's pivot back to code and do some viewing of spatial data or spatial raster metadata. So let me import OS, PyPlot, RioXarray, and EarthPy. RioXarray as RXR. Import EarthPy as ET. So we already have the data, so I'm not going to download it again, but I am going to set the working directory. I don't believe that's retained when you close the notebook and open a new one. Earth Analytics, data. Okay, so now let's explore the metadata of the raster object with RioXarray. So to start, we gotta open the data. But first we have to specify the data path with OS path join. This may seem tedious, which it very much is, but it's really kind of building muscle memory on how to do common operations. In the long run, having kind of just not even to think about that. This kind of stuff is super powerful when you're doing analyses. You can just kind of think and type as one and just get started on exploration. Not to say you shouldn't plan, but sometimes when you're just kind of doing exploratory data analysis, you just want to be able to freely investigate things and being able to know like, oh yeah, I can just invoke min and get the minimum. That's just helpful instead of having to like spend some time Googling, how do I do that? Eventually you'll kind of build up that muscle memory, and for certain common things, you won't really even have to look it up as often or at all. So let's open this data set, LiDAR DEM path, and let's make sure that we specify masked equals true. And then let's output the coordinate reference system of this data. LiDAR DEM dot rio dot crs. So we can see we get this result of EPSG 32613. Let's Google that. EPSG. It's thinking. My internet. Okay, it's struggling. Let's try it this way. That's better. UTM zone 13 north. Makes sense for like Boulder area. Yeah. Actually, where is Boulder? Somewhere around here. Boulder. Yeah, UTM zone 13 north, 32613. Cool. Let's assign this string to a Python object. So it's like a variable. So it's just easier to handle. So we can reuse it in other places. So let's set it a CRS equals lidar dem.rio.crs. Now we have this object we can invoke. In this case, we're just going to set the CRS to itself, essentially, but imagine you had data that didn't have a CRS, you can then reuse this and just kind of point and project or set the CRS. So let's demonstrate that. LiDAR DEM equals LiDAR DEM Rio. Now let's set the coordinate reference system. We're going to specify a CRS in place equals true. So this is kind of a toy example because we're resetting the CRS to the same thing it was, but using this kind of other variable, but it kind of can demonstrate that you're able to reset the coordinate reference system of data. So now let's convert the EPSG string to a proj4 string. So we can use EarthPy to do this because it contains the dictionary that'll help us convert those EPSG codes into a proj4 string. So let's do that quickly. So I'm gonna output et.epsg. Let's just see what, so we just have this huge list of EPSG codes and their associated proj4 string. So then we can use, we can basically filter down this dictionary of values by specifying the code that we're interested in. So we're looking for 32613. And this should now return just a string, the proj4 string associated with that CRS. And so you can see we have this proj4 string, UTM 13. Pretty cool. Okay. So that's CRS. And I guess before we jump to spatial extent, this proj4 string, it's telling us it's in UTM projection, zone 13, datum WGS84, and horizontal units of meters. Cool. Now let's jump to spatial extent. So it's really just the geographic area that the raster covers. So the minimum and maximum values for X and Y. It's kind of just the boundary points, basically. So if the data are not rectangular, the spatial extent may cover portions of the data set where there are no data. So imagine there wasn't any data in this they were only collecting data over the field. There would be a big chunk of no data value here. So that's something to consider. This kind of idea of extent also applies to vector data, which is something we covered in previous weeks, where you can have the spatial extent of points, and it's just the square that encompasses all those points. So let's inspect the spatial extent of our raster data. So let's do LiDAR DEM and then Rio bounds. Cool. And then similarly, let's look at the resolution. One by one. Okay. Now let's inspect LiDAR DM.Rio. Okay, no, I meant to do, okay. Interesting. I'm trying to get help on the data array.rio. like the options. I'm curious what's available. Let me just Rio X-ray. Okay. Okay, I don't actually want usage examples. There we go. Okay, so actually it's just an X-ray data array. I don't even know. A Rio accessory. Okay, there we go. Sorry if this is mildly confusing, but this is what docs look like. Um, so it's nice if you don't have to always go into them. I mean, being able to understand docs is good, but um, it's also nice if you can avoid them sometimes because they're not always the most pretty or easy to understand. All right, I'll come back next week with how to inspect that a little better. But that's actually it for this sub lesson. So let's save our changes and then commit them to the repository. Yeah, I feel like this week I mean, the lessons aren't as long as last week. It's similar content, so it's fairly chill. I don't think it's too much. It's a lot of repetition, maybe too much repetition. Okay, so we finished lesson sub lesson 3. Let's move on to number 4. Let's create a file called, actually, did I check? Oh, I didn't check. Okay, it's there. Let's create a file called geotiff.ipynb. And we're going to learn about the geotiff raster file format and how it's pretty common in Python. Okay, where did that go? Let's select the Python 3.10.13 kernel. And then let's open that data set or that lab. So I'll move it over here. So we're going to access metadata stored within geotiff files. We're going to describe the difference between embedded metadata and non-embedded metadata. And then we're going to use meta to quickly view spatial metadata attributes associated with the file. Before we jump in, I'm going to have some coffee, then we'll get right to it. Okay. So a geotiff is a standard TIFF or image file format that includes additional spatial georeferencing information embedded in the TIFF file as tags. These embedded tags are called TIFF tags, and they can include the following raster metadata: spatial extent, coordinate reference system, resolution, no data value, and how many layers are in the TIFF file. So if you'd like to learn more about the TIFF format, I encourage you to check out Wikipedia and the OSGeo documentation, but let's jump into Python. So I'm gonna move this here. So the Rio X-array package in Python lets us open geotiff files, but to also directly access the TIFF tags programmatically. So we can quickly view the spatial extent, coordinate, reference system, and resolution of our raster data. But important to note, not all geotiffs contain TIFF tags. So let's get started by preparing our work environment. We're going to import OS, Rio X-array as RXR, EarthPy as ET, And then we already have our data, so I'm gonna just set the working directory. To Earth, Analytics, Data. So now let's open the raster file that's in GeoTIFF format, basically the file we've been using so far today. So we're going to get practice using OS path join again by specifying this path. Colorado flood, spatial, Boulder, Lee Hill, RD, pre-flood, LiDAR, pre-DTM dot TIFF. Okay, now let's open it with Rio X-ray. And make sure to specify masked equals true. And then let's print out the bounds. Ooh, we got an error. And that's because I forgot to put a Rio before the bounds. Okay, there we go. So let's view some spatial attributes associated with the raster file. I believe this Rio tag is able, that's kind of how we're reading these tags. So this is stuff we've been doing already, but let's do it a little more. So pre-LiDAR DEM dot Rio dot CRS gives us the coordinate reference system. I'm going to be lazy and copy paste this first part. Rio pre-LiDAR DEM Rio node data gives us the node data value. And this is because we read in with the masked equals true, so that's why it doesn't have that -3 number. We can also get the shape like we did above or in a previous lesson. We can get resolution, and then we can get just the metadata. Or some additional metadata. Cool. So this includes information about the resolution, projection, data format, and more. Stuff we've already been kind of covering. Nothing super, super thrilling. But something that it's kind of just trying to remind you of is the importance of ensuring that both your data sets have aligned spatial metadata, whether that means ensuring they have the same projection or within the same or similar extent. These are things you can do with Python to programmatically check. So one question you might ask is, do both data sets have the same spatial extent? Let's check that with Python. We already have the DEM file, so let's load in the digital surface model. So that'll have the heights of the trees and stuff. So we can compare that with the DEM. LiDAR, DSM path equals OS path join, Colorado flood, spatial, Boulder, Lee Hill, road, pre, flood, LiDAR, pre DSM.tiff. And then let's open it with Rio X-ray. Okay, now we can use Python to programmatically check, are the bounds the same? Do both data sets have the same spatial extent? So let's do if pre LiDAR DEM Rio bounds equals pre-LiDAR DSM Rio bounds print. Nice. Else print. Bummer. Nice. Okay, so we're able to see that the bounds are the same. Let's do another comparison, checking the resolution. Cool. Same resolution. Awesome to see. So this is kind of now a quick return to the EPSG Proj 4 discussion we very recently had, but just indicating that the EPSG code is a shorthand way of specifying many coordinate reference system parameters at once. Each EPSG code corresponds to a Proj 4J code, which is a more verbose way of specifying those metadata parameters. And you can look both up online. I'm not going to belabor this point. We already did this whole kind of inspection looking up the Proj 4 string from the EPSG code, but just know that that's kind of also in this realm. So we're going to learn more about multi-band imagery in the coming weeks when we dive into multispectral data and spectral indices, but just know that geotiffs can store more than one band or layer of image data or of kind of sensor information. We've previously looked at that pre-LiDAR DEM data shape, noticing that it has the 1 by 2000 by 4000. And so another data set might have 7 by 2000 by 4000, and there's 7 layers of spectral information being collected. And so we'll kind of encounter that later on the semester, likely in 2 weeks. So that's basically it for this GeoTIFF little mini lesson. Let's save our changes, commit them to GitHub, and then continue on. I think this is lesson 4. Yeah. And then we can see that our changes have not happened yet. They're GeoTIFF. Cool. So let's jump into a test of our skills. So I'm going to touch a new file called testskills.ipy and b. Let's now open that, select the Python 3.10.13 kernel, and then open up, see what kind of test. So it's really just, let's open some data and then let's see what we encounter. And I'm not going to make you all do this by yourselves. We're going to work together. Actually, on second thought, this I will not do. This I think is a good exercise because this is kind of more similar to the final. Not walking. Let me make a markdown cell. So instructor not walking through how to do these. Please complete on your own. Good luck. So let's quickly, I'll walk through the tests, and it's not really a test. Like if you just try and do your best, like I have full faith you'll get full credit. But it's really just I want to start giving you experiences where I'm not giving you all the answers. And I think these are great for that. And so we're going to start by importing a bunch of things that we've been importing throughout this whole class, download the data, set the working directory, and then we have 4 challenges, basically. And it's all doing similar things that we've been doing up in or since like 9 this morning. So we're going to use the pre-DTM hill file, and we're going to open it using RioXarray. We're then going to plot data using this EarthPy plot bands tool, and then we're going to set the color map to gray, and also give your plot a title. So we've done most of these in class. I think the EP plot bands method, let's Google it together. So EarthPy plot bands. So, oh, great. There's this tutorial on how to use EarthPy plot bands to quickly plot raster bands for an image. So scroll down. They have this example data using EarthPy. They set the working directory. And then they use EP plot bands. So I encourage you to try and figure out how to open and plot a hillshade dataset. For the second challenge, we're going to do overlaying a DTM on the DTM hillshade. So in the above challenge, you opened up the hillshade. In this challenge, you're going to use that hillshade to create a map that looks more three-dimensional by overlaying the DTM data on top of it. And so again, you're going to use the EP plot bands. You're kind of just reusing the data from the first challenge and then just adding another layer onto the same map. Remember, we've previously plotted multiple layers on the same data set. You just need to specify AX equals AX if you're using that whole piplot subplots scheme. And your output data should look something like this, or your output figure. And note that there are some tips on how to kind of get unstuck from completing this challenge. So I really encourage you to follow those if you are stuck. But I fully expect you all to be able to crush this kind of mini challenge. Challenge 3, you're going to kind of keep building on that data set or that figure. And now you're going to add a site boundary. And remember that you can do that in PyPlot, basically setting the AX equal to AX again. And that you can also set the plotting extent so that it's nicely zooming into your data. And here again is a tip on how to set extents and overlay data. For the final challenge, this is optional, but I strongly encourage it. Opening post-flood data raster. So in the previous 3 challenges you're using, and everything we've done so far today, it's before the flood. But now it would be cool to display the DTM before and after the flood. And so you're going to display them as such using a PyPlot subplot. So these are all things that we've been doing in class. If you are totally stuck, reach out to a classmate or me, and we can get you nudged in the right direction. But I think this will be a really good kind of prep for the final and the types of things that you can expect. I think this kind of thing would be super. I could totally see something like this on the final. But yeah, let's save this and commit it to GitHub. Make sure that that got pushed. Might take a second. Yes, test skills. Okay, cool. So we have 4 more to go today. Let's get to it. I'm going to create a new notebook called Subtract Raster. And let's select the Python 3.10.13 kernel. And then let's open this link. So we're going to subtract one raster from another and then export that result to a new geotiff. So kind of creating a new file from some raster math. So the data set that we're going to be creating is called a canopy height model. So we're going to be subtracting some of those LiDAR derived terrain models to create this, namely the digital elevation model and the digital surface model. And let's jump in. I'm gonna move my tab back over here and then jump into the code. We're gonna start by importing the usual subjects or suspects, NumPy, OS, matplotlib, pyplot, Seaborn, Rio X-ray, and EarthPy. And then we'll set prettier plotting with Seaborn. Let's do the white grid style. Oops, fat fingered it. And then let's set the working directory because we already have the data. Analytics, data. Cool. Now let's open and plot the LiDAR digital elevation model. And we'll use the masked true argument to ensure that no data values don't plot and are assigned nan or no data. So let's do LiDAR DM path equals OS path, join Colorado flood, spatial, Boulder, Lee Hill Road, free flood, LiDAR, free DTM.tiff. And then let's read it in with Rio X-ray. So pools RXR, open raster IO, LiDAR DEM path, masked equals true. And then we're going to squeeze to get rid of that unneeded dimension that indicates that there's a single layer of data. Cool. Let's do the same thing for the digital surface model now, so we can do our raster subtraction. So we'll do LiDAR DSM path equals OS path join Colorado flood. So much sign, so much typing. I should not have cheated on type to learn when I was a kid. It has come back to bite me so hard as an adult working in tech. So much regret. Okay, LiDAR DSM XR equals RXR. LiDAR DSM path masked equals true dot squeeze. Awesome. Okay, now let's talk about canopy height models. So the canopy height model represents the height of trees. It's not an elevation value, it's rather the height or distance between the ground and the top of the trees or buildings or whatever object the LiDAR system detected and recorded. Some canopy height models do include buildings, especially if you're in like a more developed or urbanized area. So make sure to look closely at the data to make sure it was properly cleaned before assuming it's just trees. So we're going to calculate our canopy height model as the difference between two rasters, basically the DSM minus the DEM. It gives us the residual value or the difference between the top of the Earth's surface and the ground, which should be the height of the trees and buildings if the data hasn't been cleaned. So this method might not give you the most accurate results. There are better ways to create canopy height models using the actual point clouds themselves, but this is a good kind of first cut, and this lesson is really about kind of reinforcing raster understanding and common operations, and so it's good enough for this lesson. And so it's also just building familiarity with the canopy height model as a concept, and yeah, just more Python familiarity. So like we did in not the challenge lesson, but the lesson before that, let's write some comparisons to verify that our data are in the same spatial extent and have the same resolution. So let's just, I'm not going to do the print is the same. I'm just going to do LiDAR DEM XR Rio.bounds equals LiDAR DSM XR Rio.bounds. And if it's true, it'll say true. And if it's false, it'll say false. Awesome. It's true. I don't feel like doing the fancy print statement that's shown in the instructions at the moment. Similarly, let's check the resolution. LiDAR, DSM, XR. Awesome. True. So they have the same spatial extent and the same resolution. Great. So it's safe for us to subtract the two rasters without significant errors or uncertainty introduced. So let's, before we, actually, yeah, let's just jump into calculating it. Show how easy it is. So let's calculate the canopy height model. LiDAR CHMXR equals LiDAR DSMXR minus LiDAR DEMXR. We have a canopy height model. So now let's actually plot it. BLT subplots. Let's say fixed size equals 10 by 5. Let's do LiDAR CHMXR dot plot CMAP equals greens. And then let's do AX dot set title equals canopy height model for aggressive typing. Lee Hill Road pre-flood. AX set access off. It's thinking. So something did not work as expected. Interesting. Let's see where I messed up. Okay. Interesting. So theirs is rendering a lot more nicely than ours is. So I'm wondering if I made a typo somewhere up here. Let's double check. And if not, we'll power through. So LiDAR DEM, Colorado flood spatial boulder hill road, pre-flood LiDAR, pre-DTM TIFF. Okay, pre-DSM. Okay. So then CHM is DSM minus DEM. That's what I thought I did. Oh no, that's see look, I didn't have a interesting, so I messed up here. I said LiDAR CHM XR equals LiDAR DSM XR equals LiDAR DEM XR. So I just set them all equal to each other. That's why it looks kind of wonky. So let's reread those data in, and then we should be good to go. Yeah, so now let's do LiDAR CHM XR minus equals DSM minus DEM. Okay, this should be better. Yes, that looks much more like what is expected. So you can see, I mean, before I even go any further, that this study site might include other things besides just a more undeveloped landscape. Like this looks very much like a kind of subdivision of a suburb community where there's trees and homes, and so there might be buildings in this data set, just something to consider. Let's plot a histogram of our CHM. So you can see it might not all represent trees. There might be other things in this data set. So let's explore our canopy height model to see what might be going on. So let's get the minimum and the maximum, like we did with the previous data set. So we'll do numpy, nan, min, lidar, CHM, XR. 0. Okay, nan max, lidar, CHM, XR, 26.9. So the min is 0 meters. And then the max is nearly 27 meters, 100 feet. No, under 100 feet. I mean, that's a pretty big tree, but could be. Okay. So now that we've created this canopy height model, it's still just kind of living in our computer's memory. It doesn't exist as a file anywhere. Let's actually save that file. So let's export the raster to GeoTIFF using Rio X-Array. So data path equals OS path join Colorado flood spatial outputs. If OS path exists, data path. So you're checking if this data path exists, print or if exists, do nothing, or actually, yeah, we'll print exists, and then else we're going to make the directory or the folder exists. Okay, so it's already there. So let's make sure that our output data has a coordinate reference system and no data value defined before we save it to file. LiDAR CHM XR. Okay. NAND data. Oh, it's no data, not NAND data. Okay. It's just the no data value is none. Okay. Sweet. So let's create a path to this new TIFF file that we want to save. Pre CHM data path equals OS path join data path pre blood CHM dot TIFF. And then let's print it out. Okay, cool. And then let's actually save this data to the GeoTIFF format using the Rio Xarray to raster method. LiDAR CHMXR dot Rio to raster, and then pre CHM data path. Cool, it's done. Now let's actually read that. Let's reopen that data to make sure it works. LiDAR CHM data, RXR dot open raster IO, pre CHM data path, masked equals true, dot squeeze. Cool, it worked. Now let's save, commit our changes, and move on. You know what lesson this is at this point? 6. Okay, let's check that it committed. It did, awesome. Okay. Now let's do classify and plot raster data in Python. We're in the home stretch. Okay, so touch, classify and plot, .ipynb. Now let's open that. Where is it? Did not, no, it got created. I just don't see it. Glasses, man. Okay. There it is. Okay. So in this lesson, we're going to explore a raster and produce a histogram to define appropriate breakpoints for classification. And then we're going to reclassify the data set using a set of defined values and the NP digitize function. So we're going to learn how to reclassify raster datasets in Python. When you reclassify a raster, you're creating a new raster object or file that can then be exported and shared with colleagues and opened in other software such as QGIS, ArcGIS Online, etc. So here's like a base raster. You then have some kind of classification scheme that you're applying where you're mapping each pixel value to a new value based on some approach. And it just depends on your science question. And then you're uh, producing an output raster that is kind of classifying the original data into some kind of categories or labels. So it's really, you could break it down into kind of several steps. Data import and cleanup, which is like loading, cleaning the data, cropping, removing no data values. Then you move on to the data exploration phase, where you're understanding the range and distribution of values in your data. And this may involve plotting some histograms, scatter plots, etc., to determine what classes are appropriate. And then you actually perform the reclassification after you understand the distribution of data. There's statistical and non-statistical approaches. And here we're going to really learn how to manually reclassify using bins that we defined based off of the data exploration step. And so let's get started. Import OS, import matplotlib.pyplot as PLT from matplotlib.colors, import listed color map and boundary norm. Import numpy as np, import xarray as xr, import Rio xarray as rxr, import earthpy as et, import earthpy plot as ep. And before any of this will work, we have to select a kernel, 3.10.13. Let's also import Seaborn as SNS, SNS.set, font scale equals 1.5, style equals white grid. Then we already have the data, but let's set the working directory. ETIO home, Earth Analytics, data. Awesome. So now let's open the LiDAR CHM that we created in the previous lesson. I believe it should be somewhere. Okay. DTM path, OS path, join, Colorado flood, spatial, Boulder, Lee, Hill, Road, pre-flood, LiDAR, read, actually here we're recreating it. I guess we'll just recreate it in, I don't remember the output file. Well, let's try to read it from, I don't feel like recreating it. So we'll say a little bit of copy paste. Never hurt too bad. Okay. So we're setting the data path to OS path join, Colorado flood spatial outputs, and then the pre-CHM data path. So then let's read in pre-LiDAR CHM equals RXR open raster IO pre CHM data path masked equals true dot squeeze. And then pre LiDAR CHM. Okay. Cool. Now let's do some classification. So there are many different approaches to classification. Some use very sophisticated spatial algorithms to identify patterns. Today, we're not going to do anything like that. We're just going to be binning trees into 3 categories: short trees, medium trees, and tall trees. So to start, let's look at the minimum and maximum values in our canopy height model to better understand the range. So NP nan min of pre, so that's 0. Let's get the same value for the maximum, 26.93. Okay. Now let's plot a histogram of our data to get the distribution of values. So big X, PLT subplots, pre-LiDAR CHM dot plot dot hist, color equals purple. AX dot set, title equals distribution, raster cell, values in the CHM data. X label height, meters, and then Y label equals number of pixels. PLT show. Cool. So let's explore the histogram a little more deeply by constraining the X limits using XLim and YLim parameters. So these will visually zoom in on the data in the plot without modifying the underlying data. So let's jump in. So let's draw a histogram with custom breaks. Do F AX equals PLT dot subplots pre-LiDAR CHM dot plot dot hist, color equals purple, bins equals 0 to 5, 5 to 10, oops, 10 to 15, 15 to 20, 20 to 30. Okay. Let's set the title. And with custom breaks, X label equals height, meters, Y label equals number of pixels. ELT.show. Okay. So we're just zooming in specifically from this underlying data set only on these areas that are interesting to us. We might also want to play with the distribution of breaks. So not just using 5-meter chunks, but doing more customized bins. And so below, we're going to use the following breaks. 0 to 2 meters is no trees. 2 to 7 meters is short trees. Actually, these are probably feet. Yeah. 7 to 12 is medium trees. And then greater than 12 is a tall tree. So let's get in. Actually, these would be meters. Yeah. Okay. So let's create a histogram with custom breaks. Well, let's note that we don't have to specify the fig size all the time. That's just if we want custom fig size. Purple bins equal, let's do 0 to 2, 2 to 7, 7 to 12, 12 to 30. AX.set title equals histogram with custom breaks. X label equals height meters equals num of pixels. plt.show. Cool. So you can see that a lot of objects are in the 0 to 2 range, fewer in this 2 to 7, 7 to 12, and yet fewer in that 12 to 30 meters. So not very many super tall trees. So we've done some inspection using the histograms. Let's reclassify our raster. To do that, we're going to need a reclassification matrix, and we're going to use that same 0 to 2, 2 to 7, 7 to 12, and 12 and above kind of classification scheme to make our matrix. And so we're going to have a code where that 0 to 2 meters will get a label of 1, 2 to 7 will get a label of 2, 7 to 12 will get a label of 3, and then greater than 12 will get the label of 4. So let's create this matrix that will let us reclassify this data. So let's create an object called class bins equals. So it starts with negative infinity to 2, 2 to 7, 7 to 12, and then 12 to infinity. Let's output those bins. So now let's apply that NP digitize function and these class bins to classify our CHM. So we'll do pre-lidar CHM class X array, apply ufunc, and then we're gonna apply this digitize function on the pre-lidar CHM using these class bins that we specified. So cool, we have our classified image. Let's actually display it to our notebook. So m equals pre-lidar CHM class dot plot dot mshow ax dot set axis off plt dot show. So you can see our data is now displaying using this kind of categorical color map, but we used our kind of tree height heuristic to then reclassify this data into categories. So you can see that the areas with no trees are dark or yellow, and then they kind of become green. And so even here we can see that this color map is kind of confusing. We also have an extra class, which is kind of confusing, the missing data. And so let's do some cleaning. Let's make this a little nicer looking. And then we'll be able to make a beautiful figure with actual cool labels that we might feel inclined to share with someone else and not just hide in shame. So let's reassign the first class in our data using a mask. So that yellow junk. Let's get rid of this yellow junk here. So we'll do pre-LiDAR CHM class masked, or MA, is pre-LiDAR CHM class dot where pre-LiDAR CHM class does not equal 5. Cool. So now we have this new raster. Let's plot that masked raster. Wow, that's aggressive pronunciation. Okay. F.ax plt subplots. Let's add a fig size this time. Oops. Pre-LiDAR CHM class MA dot plot dot imshow ax dot set title equals classified plot with a color bar. Ax dot set axis off blt dot show. Okay, so it's starting to look a little better. We're getting somewhere, but we're not done yet. The glow up is coming. So let's plot this with some better color choices. Or maybe not better, but yeah, I'd say better. Yeah. Okay. So we'll use a color called linen, color called light green, color called dark green, and a color called maroon. And then let's have some class bins. 0.5, 1.5, 2.5, 3.5, and 4.5. And then let's create color map, listed color map with our colors. Oops. And then let's do norm equals boundary norm, class, bins, len colors. This is really just so that we have some nice coloring on our map with the colors that we specify. ELT subplots, big size equals 10 by 5. Pre-LiDAR CHM class ma.plot imshow cmap equals cmap norm equals norm. And then let's set a title. Classified plot with a color bar and custom color map cmap. ax.set axis off elt.show. Got a typo because I spelled color map incorrectly. And then look, we're getting there. Okay. one more, and then we'll be done with making these kind of look prettier. So let's actually make the custom legend. So it's not just a color bar, but actually specifies what the category is, like a label, a human readable label. So apologies if you can hear my stomach rumbling. Haven't had breakfast, just coffee, coffee and Python. That's all I've had today. Okay. Height, height class labels equals, and then we'll create an array or a list of short trees, medium trees, tall trees, really tall trees. Okay. Again, we'll use those colors that we did previously. Linen, light green, dark green, maroon. CMap equals listed color map colors class bins equals 2.5, 3.5, 4.5, norm, boundary, norm, class bins, len colors. Now we can plot. Subplots, big size equals 10 by 5. M equals pre-lidar CHM class ma.plot dot m show CMap equals CMap norm equals norm add color bar equals false. And then let's draw the legend. ep.draw legend m titles equals height class labels ax.set title equals classified lidar canopy height model derived from neon AOP data. AOP is Airborne Observatory Platform or something like that. ax.set axis off plt.show. Look at that beauty. Amazing. We can see how we're starting to make nicer maps with Python, which is kind of cool. You're not necessarily limited because it's code. You can actually make pretty nice figures as well. And we're just sticking to static figures. You can also do dynamic or interactive maps as well with Python. So that's it for this sub-lesson. Save our changes, commit them to GitHub. This is lesson 7. Okay. Let's make sure our changes propagated to the user interface. They did. Great. Let's create a new notebook called, what do we call it? Classify, or no, crop raster. Cool. Touch crop raster.ipynb. Okay, select the kernel. Awesome. Let's now open this lesson. So we're going to crop a raster data set in Python using a vector extent derived from a shapefile. And then we're going to reaffirm our knowledge of how to open shapefiles in Python. So we just reclassified the data, but the edges were uneven. So let's actually learn how to um, crop that classified data set. So let's go back to the code real quick. Let's load in the libraries that we'll need and then the data. So I'll start with OS. Matplotlib.pyplot as PLT using import aliasing. Same thing for Seaborn. New one today, Shapely geometry, mapping. Import Rio X-ray as RXR. Import X-ray as XR. Import GeoPandas as GPD. Import EarthPy as ET. Import EarthPy.plot as EP. And then SNS.set. Font scale equals 1.5. And then let's set our working directory to ETIO home, Earth analytics, data. Awesome. Now let's open the raster and the vector datasets. Now let's get the CHM path, open it, and plot it real quick without all the fancy labeling that we just did. Ladder CHM path equals OS path join, Colorado flood, Boulder, Lee, Hill, RG, outputs, LiDAR, CHM.tiff. Now let's open that up with Rio X-ray, then raster IO, LiDAR CHM path, masked equals true, dot squeeze. Okay, spelled something wrong. Spelled Colorado incorrectly. Okay, let's see where the code is. I don't remember. CS less spatial output outputs. Okay, LiDAR CHM. So it is there. Colorado flood, spatial. That's what I forgot. Spatial. Okay, now we're good. Let's plot that real quickly to make sure everything lines up with what we expect. Show, and then ax.set title equals LiDAR canopy height model CHM ax.set axis off plt.show. Okay, cool. It's the busted old label or the color bar, but that's fine. We just need the underlying data. Now let's open the vector layer that we're going to be using to clip. We'll call that area of interest, or AOI, is OS path join Colorado flood spatial Boulder Lee Hill Road clip extent.shp. And then let's open that up with GeoPandas. Tools, GPD, read file, EOI, crop, extent.plot. Okay, great. It's just a rectangle. Sweet. Let's view this coordinate reference systems of both of our data sets to make sure that they're the same. So let's do crop extent.crs equals lidar chm m.rio.crs. Okay, cool. They have the same coordinate reference systems. Now let's plot the data together on the same figure. So we'll do f(ax) equals ELT subplots, big size equals 10 by 5, lidar chm im plot, oops, plot.mshow ax equals ax, crop extent dot plot ax equals ax, and then let's set the transparency using the alpha keyword to 0.8. And we'll set the title, raster layer with shape file overlaid, ax.set axis off, ELT.show. Cool. We're getting somewhere. We have our canopy height model with the crop shape file overlaid. Now let's actually clip the raster data using that overlay and RioXArray clip function. So we're going to, let's just get in, I guess. Yeah, okay. LiDAR clipped equals LiDAR chm im.rio.clip. And then here we pass what we want it to use to clip. So here it'll be crop extent, and we want to pass in the geometry, and then we have to apply our mapping, which we defined up here. The mapping was, where is it? Maybe we didn't. Let me double check, but I didn't skip anything. Wait, no, we're cool. Okay. And then go back here, apply mapping, comma, crop extent.crs. LiDAR clipped. Cool. So we have this X-ray data set that we've now clipped using our crop extent. So let's verify that the clip occurred by plotting it. So fig x equals ELT.subplots, page size equals 10 by 4, LiDAR clipped plot, AX equals AX, AX.set title equals raster layer cropped to geodata frame extent, AX.set axis off, BLT.show. Pretty cool. Okay. And then if you really wanted to, you could save this data, save this cropped data, and let's do that real quick. So we'll do path to TIFF file equals OS path join Colorado blood spatial outputs, LiDAR, CHM, cropped.tiff. And LiDAR clipped.rio to raster path to TIFF file. Boom, we're saved. And then you can verify that it in fact saved by opening it. If you want, you could just do clip CHM dot plot. It won't be as pretty, but you'll see that we did in fact load this data. Okay. Now let's save the changes here, push them to GitHub, and then move on to the final lesson for the day. It's the final 5. The dream team. All right, so let's now create our final. Actually, let me double check that everything got saved. Let's get a crop raster. Awesome. Okay, now let's do a touch to create one final notebook. Touch, reproject, raster, IPYNB. Select the Python 3.10.13 kernel and just push through. We got this. So we're just going to learn how to reproject a raster using raster IO. So sometimes your raster data are not all in the same CRS. When this happens, you may need to reproject your data from its current CRS to that of another data set that you're using. But make sure you proceed with caution when you're reprojecting raster data. It's often best to reproject your vector data instead, because reprojecting raster data means that the entire data set are interpolated and cast into a new grid system. This adds error and uncertainty into your analysis. And so there's, of course, times where you have to reproject your data, but make sure you carefully consider whether you have to do this and if there's other options, namely reprojecting the vector data instead. So let's learn how to reproject raster data to another CRS using both a CRS string and that from an existing spatial layer. So let's import West, import matplotlib.pyplot as PLT, import numpy as MP, import geopandas as GPD from rasterio.crs, import CRS from, or import Rio X array as RXR, import EarthPy as ET. And then let's set the working directory to ETIO home, Earth Analytics, data. So we've seen a few different layers throughout today's examples. And so in this lesson, we're going to use Boulder County roads, which are a shapefile representing the roads in Boulder County. We have an area of interest extent polygon that represents the study area in Boulder. And then we have a raster layer for that study area. So typically when it's possible, we want to avoid reprojecting raster data because it's often easier and carries less error as compared to reprojecting vector layers. However, in this lesson, the goal is to learn how to reproject raster data. So we're going to do that. And we're going to line up the CRS of the raster layer with that of our vector data. So to begin, let's open up the road centerline data from Boulder, take a note of the CRS, and let's even plot it too. So I'm going to do Boulder roads equals GPD read file. And we're going to be using data from Esri, which is kind of nice. And we're using a GeoJSON file that's hosted on their open data kind of platform. And so the nice thing about GeoPandas is you don't have to just reference locally available files. You can also just input a URL and you'll get the data downloaded. It'll just handle that for you. So let's do boulder roads.crs. I take a second because it has to download it and then load it into your kind of computer's memory in GeoPandas. Hopefully this data set still exists on Esri's open data portal. Struggling. Dude, rude. Let's check if it actually exists. Maybe it's gone. It would be a bummer if it is not there anymore. Okay, hold up. Search. Okay, yeah, that's like not, it's not working. Okay, let's try to find, let's see if that data exists on ArcGIS online anywhere. It's called Boulder County Roads. Okay. Struggle. Okay, let's see if we can't use this. All right, let's try this random URL. I don't know if this will work. Yeah, okay, it's a feature server. Okay, this is where it gets annoying. Okay, so we'll skip the roads part because it doesn't seem like that layer exists anymore. That's cool. My bad for not checking that this morning. Um, Seems like they must have downloaded or deleted that data set, which is a bummer. Let's see if we have any other roads data in here. Colorado flood, spatial. Folder. Okay, no. You know what? For the sake of this lab, let's just I'm gonna delete this one from today's lab because the data is missing, and I don't want to have to make you all scramble to try to do it in real time. So I'm gonna remove this from the required assignment today. Cool. So I updated the what's it called? Bless up. Yeah, I updated the instructions on our course website. I'm not going to commit these changes. I'm going to delete this file actually because we don't need to submit it. You know what I mean? It's not part of the lab. So with that said, we can actually now, if you'd like to submit your lab for the day or for the week, we did everything slightly easier than last week. I feel maybe a little less content. Yeah, I mean, like, yeah, a good chunk less, but hopefully this gave you a decent introduction to raster spatial data with Python. In the remaining weeks, we're gonna continue diving in to canopy height models, LiDAR, other raster data types, and continue building our familiarity and confidence as applied remote sensing practitioners of the Python variety. But with that being said, that's all I have for today. So feel free to return to your Saturdays and enjoy the weekend. Thank you all. I'll be here for a few more minutes, so feel free to hang out and ask questions, but feel free to go home.
Thank you. Have a great weekend.
So yeah, thanks. Peace.